My name is Tony Saad, and I am an assistant professor in the Department of Chemical Engineering at the University of Utah.
And my name is James Sutherland. I'm a professor of chemical engineering at the University of Utah.
In June 2020, the Utah Symphony reached out to us seeking help to understand the risk of COVID-19 infection at one of their concert halls.
And while they had a plan for masking string instrumentalists, they were concerned about how to mitigate risk for wind instruments like brass and woodwinds that emit aerosols, which are very small droplets that can be transported. They get entrained in the air and get moved around with the air. And so they were concerned about how to mitigate risk associated with those wind instrument players.
Therefore, if we understand how the air moves, we can track where the virus goes and therefore develop potential mitigation strategies. We used a technique called computational fluid dynamics in conjunction with high-performance supercomputing to simulate the airflow in Abravanel Hall, that's the concert hall where the orchestra was playing at, and track where these aerosols move around.
And as we did this analysis, we discovered that there was a significant accumulation of aerosols in the stage area, given the proposed seating arrangement that the orchestra had planned. And so as we found that, we realized the standard 6-foot rule would not apply, would not mitigate risk effectively, and we needed to seek other risk mitigation strategies.
So our mitigation approach was based on the idea that if you change the airflow, you change where the aerosols go. Think of trying to move away from smoke, you would potentially open the doors, the windows, and move away, change where you're seated. So we decided to try to open the doors at the concert hall on the stage and also manipulate the HVAC system to develop our mitigation strategies. We also looked at rearranging the seating in the orchestra.
And as we considered how we might rearrange the orchestral seating, we prioritized putting high emission instruments near air returns so that the emissions would be entrained in the airflow and carried out of the venue rather than across breathing zones of other instrumentalists. And as we pursued this option, we predicted that we could achieve a factor of about 100 times reduction in the concentration of aerosols that people were being exposed to.
In our study, also using high-performance computing was critical to achieving the results that we achieved in a timely manner.
Yeah, in fact, high-performance computing enabled us to carry out about 50 years worth of simulation time in a matter of a week or two in order to carry out comprehensive studies of our risk mitigation strategies that we were considering.
Our study showed the important role that fluid dynamics plays in the spread of respiratory infectious disease. It also showed the importance of scientific computing and the role it plays in public health.
And working on this project was really rewarding for the entire team, not just from a professional standpoint, but also we have personal connections to the performing arts. I'm a member of the Tabernacle Choir at Temple Square, which is a performing arts organization, and several of our other team members are also.
I play the classical guitar, and one of the PhD students working on the project, he is a classical music connoisseur, and he was instrumental in helping us design the new seating arrangement while meeting the criteria for orchestral seating design.
So we just want to thank the entire team, everyone who participated in making this project such a great success, including the students, a postdoc, and as well as resources that the University of Utah provided for the computing resources.
And also the funding through the CARES Act.
Funding through the CARES Act, absolutely.